start because I don't have much time, and I may cut many details. And in the first lecture, I promised to talk about there was part one, which was conformal symmetry. So I detailed the conformal symmetry. And second part was the, well, it's an important property of CFT. And the third part was correlation functions. So I spent most of the time, of course, on the last one. Okay, so there's a property of conformal field theory which is quite often stated concerning the energy momentum tensor. Right, so what is it?
Yes.
Yes, so the energy momentum tensor, T mu nu, is traceless, so meaning that T mu mu is traceless. And first, there's energy momentum conservation. This is energy momentum conservation. So the energy momentum tensor follows from a symmetry, yes? And which symmetry? No, energy momentum tensor is the meta current of the translation symmetry. So whenever you have translation symmetry, you get the energy momentum tensor. And then I talked about conformal transformation. And so F satisfies the relation so this was the conformal transformation. So now the dilatation current. This is dilatation current. So what's the form using energy momentum tensor? Okay, so that's this. Okay. So that's because so energy momentum tensor is also a generator of the coordinate transformation. And so if you want to consider this particular transformation, the generator is going to be F nu. Right? So the dilatation F nu is X nu. So this is the dilatation current. Right. So now this conserves if you have scaling variance. Then you calculate this has to be 0 if you have the dilatation symmetry. And this is 0 generally because energy momentum tensor conserves. So this leads to this traceless condition. So it's a necessary condition at least to for the theory to be a conformal field theory. And you can generalize this argument and you can show that whenever this function f satisfies this conformal symmetry equation, then you get the traceless condition. And I will not show it here because of the time. So, okay. So this is the this is the often stated statement, and so I wanted to mention it. So now this was easy, and so now this is the most important part. So I didn't say much details about conformal field theory, and so what determines CFT? I think that's the question you want to know. And what I mean by this is how do you solve? Well, what does it mean by solving conformal field theory? Okay. So to specify conformal field theory, there are two things. First, the ingredients of conformal field theory are operators. Symbolically, I expressed it this way. So like free field theory, you have operators like any operator, like if you have scalar field phi. Phi is an operator, phi squared is an operator, and any function of phi is an operator. So that's what it means by operators. And then the observables of the theory, of course, it's correlation functions. So in the standard quantum field theory, what you calculate is the S matrix. That's the observable, right? You want to see the scattering, and then the scattering tells you the information about the interaction structure of the theory. And in conformal field theory, to be strict, there's no S matrix. But the correlation function always exists. So the intuition is, so when you talk about S matrix, you prepare particles in the infinite past and infinite future, right? But you have to have particles. But the conformal field theory is scale invariant, and then anything that has size would not exist. But to have particles, you have to have the notion of scale. So conformal field theory, strictly speaking, does not have S matrix. And so correlation functions, I introduce this notation. This is familiar from quantum field theory. And so you have operators, n number of operators. Then this is the correlation function. So I want to elaborate on these basic points. Okay, so now you have I. I put I. So this is a label to distinguish operators, right? So what would be the what would be I? Like what distinguishes the operator? Yes, scaling dimension, right? Delta. So this will be so this is the eigenvalue of the dilatation. So first, because we talk about scaling of the theory, and so it's very important how this operator scales as you change the scale of the theory. And Spin, yes, good. Yes, spin. Let's go. Because, yes, so then this is associated with, yes, this rotation operator. So these are the labels you have for the operator. So in particular, this spin structure will tell you the tensor structure of this operator. Like this operator can be scalar or vector or rank 2 tensor and so on. So these are the labels. And for example, energy momentum tensor. This is an operator, yes. And the dimension. Dimension is D, and spin is 2, and spin 2. Yeah, for example, that's the case, and so now there are two classes of operators. So the first one would be, anybody studied CFT? Primary, yes. So primary fields. Primary operators. And then the second one, descendants, right. And so all together, there's something called, let me denote like this operator. There's conformal family. So these two together forms a family of operators, which is called conformal family. So there's a parent operator, primary, and then descendants can be obtained from the primary operator. Okay, so the primary operator, what is the signature? Like, what is the most important property of the primary operator? Of primary state? Exactly, yes. So let me denote like this. So where I used state operator correspondence implicitly. If the operator acts on the vacuum and you send the location to the origin, then you get some state. And so this state is annihilated by the special conformal symmetry. And so it has the property, the delta S. Delta D, of course, is the conformal dimension. And so this S is the representation of SOD rotation. And so this is the most important property. And this tells you that primary operator is the lowest weight state. Lowest weight state. And to see if it this to see this, so descendants. So now this is 1 and 2 descendants. So descendants, how does it look like? Yes, so you act on derivatives, right? So this is the translation operator. In the okay. This would be the descendant states. So this is descendant state. And the conformal dimension of descendants in this case is conformal dimension. Right. The delta plus number of the excitations, which follows from
P is
right. So P it has this commutation relation. Right. So it increases the conformal dimension by 1. And so in that relation, I mentioned that K mu lowers the dimension. So if this state does not vanish when the special conformal symmetry is acted on, then there will be lower dimensional operators. And if it can keep on going to negative, that will violate the unitarity I didn't show. But so there must be this operator, which is killed by a special conformal, and the dimension is positive. And this one increases the dimension, so it does not violate the unitarity. Okay, so now, so that's about the operators, and then okay, now endpoint functions. So endpoint functions, first, it can be reduced to 2-point functions, yes. It can always be reduced to 2-point functions. And by OPE, yes. By OPE, and those who know those who know CST knows this acronym, but this is the operator product expansion. Operator product expansions. And roughly the structure is so operator product expansion means the product of two operator is an operator. So if you have a complete set of operators, this has to be expanded by the complete set of operators. So that's the operator product expansion. So because of this, you repeat this OPE, and then the endpoint function can be reduced to 2-point functions. And then to determine a conformal field theory, you have to know all the conformal families. Yes, first. And then what else do you have to know? Maybe because you studied, then you know the answer. Yes. Yes.
Maybe restricted constant of the 2-point function.
Yes. So this C, IJ, okay. this is 3-point function essentially. So this is 3-point function. So as you can see from this OPE, if you know this, then you can specify the n-point function. So, but this is hard. So this is the hardest part. It's hard to find all of them. And there's usually one more ingredient to construct endpoint functions. There's something else, yes? What would be the quantity? Conformal blocks. Okay, there's conformal block. I denote like ij, m, k, and u and v. Without explaining much, I will elaborate on it, but let me. Conformal blocks, and this is roughly the 4-point function. So once you have all this, then you will know the complete solution to the conformal field theory. So now, so conformal field theory does not have to be a local field theory. If it's local, then you will have local Lagrangian description, like free field theory, yes? Well, it's free field, so it's the derivative of phi squared. That's the Lagrangian. In that case, you know the complete set of operators. So this part is kind of obvious. And free field case, of course, there's no interaction, and so this will be vanishing, and so it's obvious. But like more complicated interaction conformal field theory, how do you calculate the 3-point function? You have to calculate 3-point function, right? But then what you can typically do is the perturbative calculation. But you cannot find all order solution, or even non-perturbative effect you will not know. So that's why it's very hard to findCijk. Okay, so now I explain a bit more. And because the theme of conformal field theory is that so without knowing the details of the theory like the Lagrangian, how much of CFT can be determined? That was the question. And first I have to say that C cannot be determined by conformal symmetry. I will elaborate on it. And so, I don't know how much time I have. Okay, let's see. Okay. Right. So first, I summarize. I can summarize the structure of a conformal field theory by diagrams. So there's a line connecting I and J, and this is roughly 2-point function. And so this Ij is the label. This is the conformal dimension spin. So this covers so this operator. So essentially, this is the operators. So this diagram represents operations. Now, my notation ijk. So this is a 3-point function. And structure constant. Oh, did I say structure constant? So this Cijk is sometimes called structure constant. So this is the second ingredient here. And finally, there is this diagram. There are two things in this diagram. Three things. First, this is clearly some 4-point function. So I'm talking about 4-point function here. And obviously, so these are not quite equations. I'm just defining this quantity. But this is an equation, some non-trivial equation. And there's a name. And what is the name? Eh?
It's conformal blocks.
Bootstrap. Yes. This is the conformal bootstrap. But the conformal block is very important in this equation. So this is the conformal bootstrap, and if you look at it, there's C here, and C here, and C here, and C here. And then, schematically speaking, so this quantity looks like C, C, and F conformal block. So to write down this equation, conformal block is involved. Okay, so now this is pretty much it. This is the conformal grid theory, and then the rest is how you can technically calculate all these things. But what I want to mention is one thing is, so as I will show later, the 3-point function or the structure constant part of the 3-point function, it cannot be determined by conformal symmetry. But as you can see, this is an equation which constrains C. Right? So there's more, and this equation has not a single equation, but there's an infinite series of this equation. So recent idea, one of the ideas, even from the beginning of conformal field theory, was using this conformal bootstrap. Maybe, if you are lucky, you can determine C. That's the idea. And also, you can recent studies of bootstrap is a bit different. It does not aim to find C's, but you can use this equation to restrict the conformal dimensions. So that's the thing people are working these days. Okay, so this is the summary, and if I cannot go too far, and this is the take-home message. And I wanted to elaborate on this structure of operators, but which I skipped. Okay, and so now what is important is what is important is word Takahashi identity. For conformal symmetry. So I focus on primary operators because the correlation function of descendants, you can derive it from the correlation functions of primaries. So I focus on primaries. And then, so these are the property concerning the infinitesimal transformations. And in finite transformation, these becomes this equation. This is the equation the primary fields satisfy. And this is the Jacobian of transformation x to x prime. So it's the d by d matrix, and it's the determinant. And so this implies the word Takahashi identity. So I defined the correlation functions before, and so So the conformal symmetry implies that the correlation functions have to satisfy this identity. So this is the same as this statement here. This is the property of a primary under the conformal transformations. And so the theory has to be invariant under conformal symmetry is stated in this equation. Okay, so now, well, and it's very the standard textbook thing, and you may know, and how far we can go by this identity. Yeah. So first, so translation invariance means some constraint on the correlation functions. What would that be? Yeah? Yes, but right. Okay, so this if you try to use translation symmetry to this equation, it wouldn't give you nothing.
Doesn't mean the correlation function can only depend on the difference.
Exactly, yes. So, so the correlation function can depend only on the difference. Okay, let me, so I define ij. Yes, so the correlation function only depends on the difference of 2 points. This is automatically translation value. And then the rotation means, yes, it has to be the norm. So the correlation function can only depend on the norm of the difference of 2 points. So initially, this is a function of ND variables because you have D component for each and you have N of them, ND. But then by translation and rotation, it now becomes, you pick 2 points, so 2 out of N, and so you have this number of variables. Okay, it's the same notation as this. So the correlation function depends on this number of variables. You can reduce it further, as I will discuss. So from now on, I consider scalar operators because the tensor structure is a bit complicated, and so I want to focus on the simplest structure of the correlation function. Okay, so now there are famous statements. So I consider a focus on scalars. And now there's 2 and so I want to discuss 2 and 3 and 4 point functions. Okay, so this, you may know the answer. So the 2 point function, using this Wald-Takahashi identity, so use WT identity, you can show that 2 point function has to have this form. I don't think I have time to show it, so I just state this. But it's a good exercise, and I recommend you to work out. So using dilatation restricts the form of this, and then next you use special conformal transformation to find these conditions. That's the idea. sorry, I should have put 2. And next 3-point functions. This gets restricted to the following form. It has to have this form. The derivation is the same again. You use dilatation and special conformal to find this. And so this is the structure constant I mentioned here, this C. And this is undetermined. So that its dependence on the coordinates is determined this way, but this is unknown. Or, I mean, by conformal symmetry, you cannot tell what this value is. But what about this one? Yes? Yes. So this is a normalization, and we don't care much. So we normalize it to be 1. And it also, you could have different operators with the same conformal dimension. And so you have to diagonalize. So because, so this set of operator forms a matrix, right? And so this would be in general some non-identity matrix. But of course, by change of basis, you can always diagonalize it. So there's another, so this thing too. And then 4-point function. Is a bit more complicated, and J this is the 4-point function. So the space-time dependence is fixed like this, and then there is this function, and U and V are called cross ratios. Yes, cross ratios, and so U in my x2 squared, x4 squared, then x1 3 squared, x2 4 squared. This is U, and V x2 3. x1 3 and x2 4 squared. So these combinations are special because yes, this is invariant under conformal symmetry. So that's why you can't determine this function. So there are two, U and V, in the case of 4-point. But the conformal ratios, if you go to higher point functions, 5 and 6, you will have more, right? So what is the argument? So I wish to, so I want to elaborate on cross ratios. So the number of cross ratios in n-point function is this. So in particular, n equal 4-point function case, you have this is equal to 2, that is u and v. And then, so you can find this number by using conformal symmetry. So you start from set of points. So initially you have these points, right? So now, okay, let me, I want to focus on x4 and xn. So first, use translation p mu. Then we can set x4 to be 0, right? So I use translation. Then I kill this one. So now, next, use k mu, special conformal. So here I want to mention one thing. So I didn't explain before, but the special conformal transformation has this property. This is the transform coordinate, and this is the original coordinate. So it has the property that k mu is an inversion. So inversion in the sense of this, right? Invert plus shift. So C mu is the shift. So the special conformal transformation consists of two distinct transformations, inversion and shift. So now, using inversion, I can send x4 to infinity because I invert 0. Now, once it's infinity, whatever you do, it's infinity. So you don't care. So next, by shift, I can bring x1 to 0. So you killed x4 and x1 this way. And now you can use rotation to bring, let's say, x2 to be the x-axis. Because you rotate and you bring x2 to align with the axis. So then it takes this form. And then finally, using dilatation, you can set this to be a unit vector. Right, so now, yes, I should be finishing. Okay. Really? No, I have a bit of time. So what I wanted to say was, so now I killed 3 coordinates. So you now have n minus 3 variables. So you choose so this is the choice 2 out of n minus 3 points. So that's the difference of coordinates, right? So I fixed x4, x1, and x2. They are fixed. And the rest is not fixed. And so you have first the choice of this much because you have n minus 3 variables and you have to choose 2 of them to combine to get this xij. So you need xij, right? And then now infinity does not matter, but you can you have finite x1 and x2. So this is the choice of I and let's say 1, and then you have another choice I and 2. So this would be xi1 and this would be xi2, and so you have xij here, xi1 and xi2, and xi4 does not matter because it's infinity. It should drop out. So altogether you get this number of independent variables. So this would be the number of conformal ratios. So that's why from the beginning, you should have expected that the 4-point function cannot be determined due to this ambiguity of the cross ratios. Right, okay. Let's see, what can I do? So now I should wrap this up. Okay. How much time do I have?
5 minutes.
5 minutes, okay. Alright. So clearly I don't have time to show all of this, but let me say now I want to mention OPE and conformal block, etc. OPE. So when I discussed the basic ingredient of correlation functions, I used OPE to reduce n-point function to 2-point function. And then in that argument, I emphasized the importance of structure constant C, which would be the ingredient. And I was very schematic at that point, but now I want to make it a bit more precise. So times x2. This is the form of operator product expansion, and this CK thing x12 delta k delta I minus delta j, and times you have structure like this, xy2 so this just follows from, okay, first, so these are descendants. And so this is primary. And this factor follows from the counting of dimension. So the left-hand side and the right-hand side has to have the same dimension. So you have delta I, dimension delta I, and delta j. And the dimension of coordinate is -1. Right? And it has dimension, this one is primary, and this one has dimension delta k. And to compensate the difference of dimensions, you have to have this one. And second, this has to be a scalar quantity. So that's why you have to contract indices. And it's a function of difference of x1, 2. And then this derivative of this, sorry, here's a 2. And I should have put like this 2. So this derivative gives you the descendants because right. And this lambda ijk is what I called as C. So this is unknown. Can't be determined. By conformal symmetry. So conformal symmetry does not fix this one, but this determine. Okay, I don't write down the equation, but the argument is, so you use this, and then you consider 3-point function. Then what you will find is this lambda is this structure constant, and the rest is just this function, you know. So this can be determined. Right, okay, so finally, using this OPE, I write down the 4-point function. So now I apply this OPE to 4-point function. So I have I, x1, j, x2, k, l. And so if you use this, CM, acting okay, what I have done here is I took OPE here and here, and then this reduces to 2-point functions, and then I use 2-point function here. So this is 2-point function. And so roughly there are a bit of ambiguity in defining conformal block, but this is essentially the conformal block. So this is the conformal. So sometimes people multiply these factors, and you have to, yeah, so up to these factors, this is the conformal block. But as you can see, conformal block, you know what it is from conformal symmetry alone. Because what you don't know is these lambdas. That's the only thing. Okay, so now here's the thing. I could have taken OPE here first, and also here, and then use 2-point function. So that was this equation. So here I did ij, and then I have m and kn, and then this is the first one. And second way of doing will give me so jk and il and some summation over m. So this was the conformal bootstrap I mentioned. Or, so often people call, so this is also crossing symmetry. It's a consequence of crossing symmetry. There are other names, crossing symmetry, or associativity. So the point here is when you calculate this correlation function in the path integral, you have the insertion of these things, right? But the order of them doesn't matter. There's a permutation invariance, so I used it. And so you can show that this is the same as this consequence, that when you have three operators, if this operator is associative, which means you can calculate this first and then you can multiply this. Or you can first multiply I and j and then multiply this. And usually you have this associativity. And from here you can derive the same equation. And that I don't have time, I don't work out. So one is not associative, as far as I know, it's like an octanion. Like you have numbers, like a real number, complex, and then you have quaternion, and then there's one more, which is called octanion. That strange number does not satisfy this associativity. But that's the only example I know, which is non-associative. But for this standard quantum field theory, the operators are associative. Apparently, this multiplication you can do this way or not this way. It's the same. Okay, so as I mentioned, there was that diagram, and here you have lambda, actually lambda, and you have this conformal block involved, as you can see from this. And then this will give you some constraint on the structure constant. Yeah? Right, so if you get interested in it, then you read the reviews and study more on the recent topics. Okay, thank you.